And I'll have to check on it. There was only one Cal 2 available for me, and it is a Tuesday, Thursday, but I believe it's a 9 a.m. I have to double check. So just so you know, I am going to teach at least one Cal 2 next semester. So you can avoid me or take me if you pass it. I think it's at 9 a.m. on a Tuesday. I'm going to have to double check though.
Not really, actually.
All right, so we are going to start a new section today, 3.5, inverse trig functions. Now, inverse trig functions were studied in pre-cal, and you may have seen a slightly different notation for inverse trig functions. So let me start off with an example here. Y equals sine x. You know, we know that that's a nice, smooth, continuous sine curve, right? That's what sine was. And then in pre-cal we said, well, wait, you know, I wonder if there's a way we can come up with a function that's the inverse of that. That would basically undo it, right? So we came up with it in pre-cal and we called it the inverse sine. We wrote it like this, or you wrote something like arc sine of x. Depending on your instructor, they may have used this notation or this notation. I'm going to almost exclusively use this notation. All right? We use that notation a lot because it doesn't have the superscript, right? With the whole idea of like this is easier to type than it is to type this, that sort of thing. But when we did this in pre-cal, what we realized is that to have an inverse function, you cannot just define an inverse function on the entire domain of sine because sine fails the, what do you call it? For a function to be a function, it has to pass the vertical line test. For it to have an inverse, it must pass the horizontal line test. It does not. So what we do for sine is we cut it. Do you remember cutting it in pre-cal? You just like restrict the domain between here and here, between negative pi over 2 and pi over 2. And if you just look at the sine function on that restricted domain, then it does pass the vertical line test and the horizontal line test, and then you can define an inverse function on that one section. And, pardon?
I did this homework.
You did that homework? Ooh.
I did the wrong homework though.
Yeah. You were supposed to do 3-3. Was it 3-3 or 3-4?
This is 3-5.
Yeah, this is 3-5. 3-3. Okay.
Oh.
So you're ahead of the game, I guess. But make sure you go back and do 3-3. All right. So in pre-cal we define the inverse trig functions, all of them, right? There's 6 of them. And all of them have different domain restrictions. And I'm not here to go rehash all that. I just want to make sure everyone's aware that the inverse functions can only be defined for trig functions if there are those domain restrictions. The first section of this homework assignment for this 3.5 is going back and asking you to find, like, you know, what's arc sine of this, and so it is a review of pre-cal. And then later on in the homework, you have to start taking derivatives of these functions. All right. So I'm not going to spend any time on this. Just when you do the homework, I kind of go through it slowly, see how that goes, and if you have any issues, you know, break out your pre-cal notes, see if you can make sense out of it.
I was curious as to why you only had 7 views, and I was like, because you usually get over 100.
It was, yeah, you were ahead of the game. All right. So today is about derivatives, right? Just like last time, what we did was we spent time defining the derivative of logs and exponential functions, right? And we also use this new technique for differentiating called logarithmic differentiation. So that's what last class was about. Today, we're going to find the derivatives. What are the derivatives of the 6 inverse trig functions? And here they are. These are listed in the book. They're also on your formula sheets. And what I'm going to do is I'm going to start today by showing you why this first one is this. All right? And I'm going to put a star next to this one because this is a very important derivative to know. It comes up a lot in Cal 2, and so does number 3. Number 3 comes up a lot in Cal 2. The others, they do appear, but not as often as those two do. So I'm going to show you the first one, all right? So how could we convince ourselves that the derivative of the inverse sine is 1 over the square root of 1 minus x squared? I mean, it seems weird. I mean, maybe you agree. The derivative, what's the derivative of sine x? Cosine x, right? So the derivative of a trig function turned out to be a trig function. But the derivative of the inverse trig function turns out to be this weird, like, rational function. Not really a rational function because it's not a polynomial, but it involves a ratio. You got square roots, and there's no trig in here, right? There's no trig in this. But there is, and I'm gonna show you where it all comes from, all right? Not going to use circle, but it's tied to it, yes. All right, so let's start with this. I'm going to prove this right to you right now. I'm going to say, let's let y be equal to arc sine of x. I want y prime, right? I want the derivative with respect to x of this. There's the answer, but I don't know that, right? I'm pretending I don't know. So what I'm going to use is what I learned in pre-cal, and that's if you put sine together with arc sine, they wipe each other out. That's what inverses do. So I'm going to take this equation right here. I'm going to take sine on both sides of this equation. So I'm going to take sine of arc sine of x over here and sine of y on the left side. Now, so long as the domain restrictions are met, this right here should turn into what? X. Right, so the right side should turn into x. So I want to put a little asterisk here. I'm not going to be testing you on the domain restrictions. I just want to be clear that the only way that this turns into x is if the x is restricted properly. Okay, if x is outside of the domain of the arc sine, this formula doesn't work. So we are assuming that this x does lie within the domain of the arc sine. So if you go back to pre-cal, that x has to be between -1 and 1. Because that's the range of the sine function, right? Sine goes between -1 and 1. So the range of the sine function becomes the domain of its inverse, and they switch places. So the domain of this is between -1 and 1. Again, let's not get caught up with technicalities. Let's just move from here to here. We okay with that? All right, now why did I do that? Well, the reason why is because I know the derivative of sine, right? Derivative of sine of something is cosine. So that's why I made this switch. So what I'd like to do now is take the derivative implicitly, that means on both sides, with respect to x. So what is the derivative of the left side of this with respect to x? Be careful. Cosine y times dy dx, I'm going to write as y prime. Is that all right? Good. Very good. That's what I wanted to hear. That's chain rule on this. Are we done on the left? Yes. Equals 1. Okay. What was I trying to find? Y prime. So let's solve for y prime. Let's divide both sides by cosine y. And that could be the answer. All right, but there's one little issue here. And the issue is that our answer has y in it, right? We'd prefer it to have x, because all of our derivatives of functions of x have been functions of x, right? Like if I take derivative of x squared, the answer is 2x. If I take derivative of sine x, it's cosine x. We've never had the derivative of something with x's in it have y in the answer. So I need to know what cosine y is. Actually, I need to know what 1 over cosine y is. So this is where you're going to have to remember something in pre-cal. And we'll kind of take baby steps here. We wrote down something earlier, right? We had a line I've erased here that said this. It said sine y was x. Do you remember when I took sine on both sides? We had that up there? All right. I'm going to draw something, and you tell me if you agree with this or not. I'm going to draw a right triangle. I'm going to call this angle right here y. And then I'm going to draw, I'm going to put over here x, and I'm going to put over here 1. All right? What is sine of y on this triangle? Sine is always the opposite over the hypotenuse. What is sine of y here? X. Do you see how this triangle matches this equation? Do y'all see that? We call this a reference triangle. We start with this equation, and I create a reference triangle from it. Now you could, if you want, look at that x as being x over 1, and that might help you see it a little better, right? Opposite over hypotenuse. So I can create this triangle based off that equation. Now, why would I do that? I want to know what cosine y is, don't I? And now I can come back to this and I can figure out what cosine y is. Cosine y off this triangle is adjacent over hypotenuse. But you need to know what adjacent is. You have one side here that you need. You do have the other two sides, right? So why don't we just call this for now A for adjacent? Is that all right? A. By the Pythagorean identity, a squared plus b squared must equal c squared. And I can solve for a, right? Just move this over here. I get a squared is 1 minus x squared. Take the square root. And I should have plus or minus, right? But length of a side of a triangle, I'm going to look at this as being a positive answer, so I get this. You all there? You got it? So if this side of this triangle is square root of 1 minus x squared, then cosine y would be this over this. 1 over cosine y would be the reciprocal. So it would be what? This over this, wouldn't it? Let me do it a little different. Cosine, 1 over cosine is secant, right? That's secant y. Secant is hypotenuse over adjacent. So if I write that down, I get 1 over square root 1 minus x squared. That's it. Does that make sense? So to prove these, okay, to prove each of these formulas, what you would have to do is start with your equation, come in with the inverse trig function on both sides, implicit differentiation, reference triangle off of the equation you started with. Well, not the original equation, when you came in on both sides, and then work with that. I'm going to do one more. Let's do the other one that's real important. The derivative of arctangent. So let's say that y is equal to arctangent of x. I want to find y prime. The answer should be 1 over 1 plus x squared. So start with this equation, and what should I do? Tangent on both sides, right? Now be careful with the way you say that, because we're not multiplying both sides by tangent. We are taking tangent of both sides. It's tangent, tan by itself is not a number, so you can't multiply. Does that make sense? You're doing the function on both sides of the equation. You're not multiplying. You're composing both sides. And actually, it doesn't. It's not even that. It's this. It's because if you have y equals, let's say, tangent x, and that means that x is equal to arctangent of y. If you have a function and its inverse, then tangent, let me say it this way. Let's say we have this right here. And let's say that you've restricted it so that it has an inverse. Then x equals y is if and only if tangent x equals tangent y. It's saying this. It's saying that if you have an equation, left side's equal to right side, if you take tangent of the left side and take tangent of the right side, you'll maintain equality. That's what we're using. The equality is held. And that's what we're doing here. We're saying we had an equation, right? And because this is like something equals something, then tangent of that something will equal tangent of that something. It's not multiplication. It's not even like multiplying by a function. It's just like,
adding that invisible one.
it's not. It's not an invisible one. That's what I'm trying to point out. It's not an invisible one because it's a function. I'm trying to think of a better way I can explain it. Let's say I tell you that x is y. Everyone, x is y, all right? Then do you agree that if I square the left side, it should be the same as squaring the right side? Okay, what did we do there to do that? Like from here to here. We squared both sides, right? We square both sides. You've been told that that's okay. When you square both sides, are you multiplying both sides by the same thing? No. You're doing something to both sides, right? You're doing an operation on both sides. And then you can look at that operation as being a function. You are squaring both sides. Here, we are tangenting both sides, if that makes sense. But it's not the same as this. X equals y, 2x equals 2y. There, I multiply both sides by 2. That's an algebraic operation that I did, right? It's just multiply left side by 2, multiply right side by 2. We maintain equality. That's different than this. But they still maintain equality.
So it's kind of like maintaining square root on both sides.
Square root on both sides, same thing. Yes, you're doing an operation on both sides of the function, or both sides of the equation.
So tangent is an operation.
It's an operation, yes. It's a function.
A functioning operation.
All right, what happens now? This tan inverse is going to be gone, right? All you're going to get is the x, so long as your domain restrictions are appropriate.
And then we get our triangle like out of nowhere.
There's your triangle. Your triangle will come from this, but we're going to differentiate it first. So let's differentiate it. So if we differentiate this with respect to x, what will we have? Did I record? Yes, I recorded.
Square dy dx.
Secant squared y, right, is derivative of tangent y. Secant squared y times y prime equals 1. Solve for y prime. 1 over secant squared y. What is secant by definition? Secant is 1 over cosine, right? So watch how I do this. I'm going to write this as, let's see, is this the same? Ooh. Is this the same as this? It's an S. Are those the same? Yeah, if I square 1, what do I get? 1. If I square secant y, I get secant squared y. What is 1 over secant? What is 1 over secant y? Cosine y. So this is cosine y squared, right? So I'm going to put squared there. So in order for me to know what the derivative of arctangent is, I need to figure out what cosine squared of y is, or what is cosine of y squared. Where did that come from?
So, it's 1 minus x squared square root. So
Yeah, well, we need to go to this to get our triangle, right? We're going to draw our triangle off of this. So my reference triangle, the angle inside of it will be what? Y, right? Because look at my trig function, this is the angle. And then tangent by definition is which side over which side? Opposite over adjacent. I look at x as being x over 1. So this is x and this is 1. Right? Then to get this side, which I could call C, or H for hypotenuse, or anything I want, I would figure, oh, why am I going to find C, by the way? Because I need cosine, right? Cosine of y would be adjacent over hypotenuse, and so I need that, don't I? So let me go ahead and use my Pythagorean identity here. I know 1 squared plus x squared must equal c squared. Root both sides. So c is root of 1 plus x squared. So this side is root 1 plus x squared. And now I'm ready to put this together. Y prime will be cosine of that triangle. So 1 over square root of 1 plus x squared. But all of that, what? Squared. And when you square the top and bottom, you square the top, you get 1. You square the bottom, you get 1 plus x squared. So this is equal to 1 over 1 plus x squared. And that's what it says on the formula sheet, right? All right, so all that, what I just did is just to show you, look, that's how those formulas are obtained. What we need to be able to do is use them to take derivatives. So let's take some derivatives here. And like we did with the logarithms and the exponential functions, we're also going to have to always be mindful of product rule, quotient rule, chain rule, all of that's in play, right? So if you wanted a formula kind of like, I don't know, I don't think I did this for you last class, actually. I did not. Let me do this just so you have it, okay? Last class we learned that if you have a to the x, what was the derivative? A to the x natural log a, right? That I gave you last class. What I didn't give you, I'd like to add to this. I'll do this in a different color, even though it's not going to come up on the camera. If I have a to the u, I don't think I gave you that, right? Okay, so let's say u is like, u could be anything. It could be, you know, sine x. It could be anything we want. Then if I take the derivative of this, it's itself times natural log of a, right? But then you always have to tack on the chain rule times the derivative of what's up here, which I could write as u prime. See, up here we did the same thing, didn't we? But what was the derivative of what was up here? It was 1, which means we didn't write it. But if you want a more general formula, this is it right here. Now, in the case that you have e to something, it's a very special case of this, right? It would be e to the u. The derivative of that would be itself times, and we would not have to do this part, right? Natural log of e would be 1, so we wouldn't need that part in here, right? Natural log of e is 1. So I don't need that, but I would still need the derivative of what's up here, so u prime. So these two formulas are very general formulas for the derivative of any exponential function, and then specifically the derivative of the natural exponential function. We could do the same thing with the logarithms. I said if you had log base a of x, the derivative of this was 1 over x times natural log a. But if we generalize it and we do log base a of u and take the derivative, this time u can be anything. Then it'll be 1 over what? U ln a, right? Times the derivative of the u. So that's your chain rule happening. See, every time something out here pops out, it's the derivative of what's inside the log. So that would be a more general formula for the log. And then if we do the very special log, that's natural log, right, of u, then the derivative of that is just 1 over u, and we don't have to have that natural log a part in there. But then we still need what? the derivative of u. And a lot of times, people will put the u prime on top of the u like that. Because that's what that is, right? Just pops up there. So if you have the natural log of some junk, the derivative of it is the derivative of the junk over the junk. The derivative of the junk over the junk is the derivative of natural log of junk. All right, now with this said, I hope you followed this. Do you all kind of get this? Yes?
Can you add this to our formula sheet?
It's on your formula sheet. What do they use as the letters?
They've just got e to the x, they've got absolute value of x, natural log.
Let me see. Yeah, they don't have the chain rule incorporated there, do they? Let me think about that. I'll think about it. All right, see, because this goes back again to, I think we were talking about this at the end of class. If I say what's the derivative of sine of x, everyone's going to say cosine x. But it's understood that there's really a times 1 out there because you have to take derivative of what's in here, right? So the formula sheet is written with the understanding that you get chain rule, okay, that you get it. These formulas are written if you're still kind of needing to have that additional little reminder that chain rule is always there. Does that make sense? So let's look at the formula for arc sine the way it's written. The derivative of arc sine of x is 1 over the square root of 1 minus x squared, right? That's the derivative of the arc sine of x. If we were to generalize that, and instead of using x, use u, it would look like this. Derivative, sorry, I forgot to put derivative here. Derivative of arc sine of u would be what? Square root of 1 over 1 minus u squared times, here's your chain rule, derivative of u. So there's that piece popping out again. That piece right there. That was a 1 up here is a u prime here. We use a u instead of an x to kind of remind you, hey, look, that thing in there could be like something other than just x. And then you have to account for it in the chain rule. All of those other formulas could be rewritten generally like this. Every single one of them, you'd replace all the x's with u's, and then you just throw a little u prime at the end. So I'll do the arctangent one underneath this. If we have arctangent of u, the derivative of it will be 1 over 1 plus u squared times u prime. And you could slide that u prime on top if you wanted. On both of those, you could put the u prime on top. Now remember, there's 4 other formulas I haven't even talked about, right? I didn't prove to you or anything. But they're there, they're all fair game. So let's go ahead and do a problem. Let's do an example. Which one? What do you mean? That's a formula. We'll use the formula to do a problem. All right, here we go. Let's find the derivative. Let's find the derivative of y equals arc sine of root x.
Is there an advantage? It's really simple. Just a notation question about using sine to the -1. Is there an advantage of using that versus arc sine?
Advantages, I don't think that there's an advantage to using this over the other one. The other one, I think you could argue, might be preferable because when we see -1 as a power, we always think that means 1 over. Right? Like if I write x to the -1, everyone knows that's 1 over x. But when I write this does not mean this. This is cosecant, and we have a different notation for cosecant. This -1 means inverse. It's one of those places in math where our notations actually clash. and you have to understand the context of what you're looking at to understand what they mean. This means negative power, 1 over. This means inverse function. So that's why I would say that this notation is somewhat frowned upon, but that's why I use it so much, because I want people to understand it's not this. All right? It is an inverse. So let's do this one. I have arc sine of u, right? Arc sine of u. The derivative of that should be 1 over the square root of 1 minus whatever this is, right? Root x squared, which is going to be x. And then times the derivative of what's in there. 1 over 2 root x. We've done that many times. 1 over 2 root x, like that. Then you could even go in there and say times 1, yes. All right, let me try and clean this up. I have 1 on top. I have root. I have 1 minus x. That's what this is. And then I have times 2 root of x. I could go a little further if I wanted to, because this is multiplication. I could put the 2 out here. And then if I have if I had like root a times root b, I could turn that into root ab, couldn't I? I could put both the roots together. Because it's multiplication, I can do that.
As long as you keep the parentheses.
With where?
On that other one, it's got 1 plus.
It's got 2 terms, yes. So what I'm going to do is I'm going to put these 2 together, which means I'm going to take this piece and multiply it times that piece. And when I do that, I get x minus x squared. So I'm going to distribute that x through.
The x squared come out would just be x.
You cannot take the x squared out because it's subtraction. So, and you cannot split that into 2 roots because it's subtraction. So that's it. Questions? Sure? All right, let's change the problem a little bit. How is that different?
Well, it's in a function.
The arc sine lives inside of a root, and so you've got chain rule here, right? You've got a function inside of a function. The outer function here is the root function, right? The outer one is the root function. So if I take the derivative, I take the derivative of the square root of something, which is 1 over 2 roots of that something. That looks ugly, but that's what it is. Times the derivative of the stuff in there, right? The derivative of this. And what is the derivative of arc sine of x? 1 over square root of 1 minus x squared. You could put those 2 roots together, couldn't you?
No.
Now, I probably won't. Shit, got a cramp in the arch of my foot. What the hell? Okay, it's gone. Guess I'm not drinking enough water. All right, so there's... The reason I would not put those under the same root, it wouldn't be wrong to, is that by me putting them together, it's not going to get any cleaner. Like on the last one, we put them together, it became x minus x squared under the root, because they were both polynomials, so it was nice. This isn't really going to get any cleaner. So it's really up to you. What do you want? Leave them apart, put them together. Leave them apart. Arc sine x, 1 minus x squared. Good enough. All right, let's try something else. X arc cosine x. Product rule. Good. You want to see the product right here? So your derivative will be derivative of the first one times second plus blah, 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 right? 1 times arc cosine x plus, what's the derivative of arc cosine x? Minus 1 over, or negative 1 over, square root of 1 minus x squared. That's almost the same exact derivative as arc sine, except it's negative.
Can't you just go ahead and drop the negative out?
You can put the negative out front, make it a minus. You could. I have to finish product rule off and put that x there. So there's you're completing the product rule. I don't see much that we can do with this. We can put arc cosine x minus x over square root of 1 minus x squared. Looks good to me. The book might, but I don't think so. On the homework solutions for this, I think I tried to match the book on most of the problems just to mess with some of the algebra.
One of them took you like 10 minutes.
Yeah, one of them was pretty long. It was pretty long.
I was like, I'm not doing this. So I just answered
What?
the next problem.
At least he's honest.
I
Yeah,
was like, oh my god, this is so long. I don't want to do this.
He's like, nope, not gonna do it.
not happening. I hope that you see that all we've done is just added 6 more derivatives to our toolbox of derivatives. That's all today is about, at least this part of today, all right? Last time we added exponential and logs. Today we're adding inverse trig function derivatives. And there's another set of derivatives that we will need to learn, but usually we do that in Cal 2, and that's hyperbolic functions, hyperbolic trig functions. So you have, how many of you, I doubt in pre-cal you saw hyperbolic, right? So there are 6 trig functions: sine, cosine, tangent, cosecant, secant, cotangent. 6 trig functions. We know the derivatives of each of those, right? Off the top of our head. Derivative of sine is cosine, derivative of cosine is negative sine, derivative of tangent, secant squared, cosecant, negative cosecant, cotangent, secant is secant tangent,
Whatever you say.
cotangent is negative cosecant. Okay, so those 6, for each 6 trig functions, we have 6 derivatives. Then there's the inverse trig functions: arc sine, arc cosine, arc tangent, and there are 6 derivatives for those. And then there are 6 more trig functions called the hyperbolic trig functions: hyperbolic sine, hyperbolic cosine, hyperbolic tangent, hyperbolic cotangent, all 6 of them. And then for each of those, there's 6 derivatives. So in Cal 2, you will study the 6 hyperbolic trig functions, but it'll be more like, here they are, you've never seen these before. Welcome, introduce you to these. And then here are their derivatives. All right? And after that, we pretty much have the entire arsenal of functions that we can differentiate, and we pretty much have everything we need. All right, let's try something else. I have no idea what's going to happen here. Let's try this. Tangent of x plus tangent of 1 over x. Sorry, arctangent. I don't got what day I'm on here. Arctangent of x plus arctangent of 1 over x. Take the derivative. So what do you see here?
I see 2 separate equations, so we can do
Mm-hmm.
the derivatives.
Yeah, because you have addition, you can do them separately. This first one's pretty clean.
Just 1 over 1 x plus x squared.
1 over 1 plus x squared. That's the formula that's right out of your formula sheet, right? There's no chain rule here. Well, there is, but it's 1, right? Derivative inside's 1.
Plus,
So that's it for that. Plus, but this one's a little different. 1 over 1 plus, because it still is the derivative of arctangent. But the thing that's being squared is not x, it's what? 1 over x is being squared. Right? That's what was in here. But times the derivative of this needs to pop out of the side of this because it's a chain rule on that one.
-1/x².
Very good. -1/x². You know how I told you everyone here should know the derivative of this is 1/2 root x? And you should just know that because it happens so much? The derivative of x to the -1, which is the same as the derivative of 1/x, is another one that happens a lot. And you should just know it's this. But how do I get this?
Well, you just...
You could use quotient rule.
Well, I just use the power rule.
Power rule on this.
Yeah.
-1 comes out. Subtract 1. So you get negative x to the -2. Then drop the x to the -2 down, you get this. We good?
We can leave it as the x to the -2.
Well, I'm going to do some work here. I'm not done. I'm going to try and clean this up. Yeah. So this is going to be 1/1 plus x² plus, oh no, minus. Why is it minus? Minus, because this negative right here is going to go to this, and then I can put it out here as a minus. That all right with everyone? 1 plus, what is 1/x²? 1/x². But then times, on the outside, 1/x² like that. Is that all right?
They cancel each other out?
How do you mean?
Can you just cancel each other out? Like, how much can I get?
This, look at this right here. I'm going to do 1 times 1, right? And here I'm going to do, can I do this times this?
Yeah.
Yes, go ahead and do that. Do that times that, and then do this, distribute it through. And what do you get when you distribute that through? x² plus 1, don't you? x², 1/x² times x², the x²'s cancel, you just get a 1. So I have 1/1 plus x² minus 1/x² plus 1. And they have the same denominators, don't they? So you can add them together. And when you add these two together, 1 take away 1, you just get, what?
0.
What?
We never get zeros.
That's weird. That hasn't happened before, has it?
Since
We're saying that the derivative of this function is 0 all the time. We have to look at that function, right? We can't not look at that function. That means the slope of the tangent line is always 0.
So it's a constant?
What? Okay, I'm going to have this graph this for us. All right, it's arctan of x, right? Plus
Yes.
arctan of 1/x. And does anybody have a guess as to what this graph's going to look like?
It's going to look flat.
It's got to be a flat, it's got to be a horizontal line.
Has to.
Because the only function out there that has a derivative of 0 all the time is a horizontal line. Has to be flat.
Some sort of constant.
Oh, but maybe not.
Whoa. So what is it at 0 then?
At 0, it's undefined. Why is this function undefined at 0?
Cosine over cosine.
I need a bigger, let me make this bigger. There we go. Look at, get out of here. Okay. Why can't I plug in 0?
1/0 is undefined.
The function's not defined there. The original function is not defined at 0. So we throw 0 out. If I plug in an x value that is negative, it's going to be down here like this. If I plug in an x value that's positive, it's going to spit out this flat line right here. This line that goes straight up right here is the computer's doesn't have the ability to figure out what's going on, right? I think, did we talk about this? Computer freaks out, goes, I got to get from here to here, and it just draws a straight line up there, and that's what it does. So this is like a piecewise function, it's like a step function. But notice that on either step, this one or that one, you're always horizontal. So the derivative is always 0, as long as where you are is in the domain of the function. So anywhere except 0, We go there, the slope tangent line is 0. Weird function.
What is the arctangent graph?
Arctangent by itself, you can actually answer that. Do you know what inverse functions look like in general? They're close. So let's say I have a function right here. I'm going to draw it in purple. Let's say I have a function that looks like this. First of all, is that a function?
Yes.
Passes vertical line test? Yes. Does it have an inverse?
Yes.
Yes, because it passed the horizontal line test. The graph of its inverse must look like the reflection of that graph over that dotted line. It's the reflection of that graph over the identity. So the inverse of this function, if this is f, its inverse would look like this. I'm going to try my best here. Gosh, not great, but that's what it would be. Okay, so if you tilt your head, it's a mirror image of itself over that. Okay? So if you now want to know what the inverse tangent looks like, you have to first know what tangent looks like. And tangent is periodic between negative pi over 2 and pi over 2. And it repeats itself. So tangent looks like this. That's tangent x. And it continues. It does another one. But because we're talking about arctangent, we have to restrict the domain. So we cut off everything out here, and we just look at that one period of tangent. That is, I keep on wanting to say 1 to 1. That's what it means for a function to have an inverse. It's 1 to 1. Passes both vertical and horizontal line tests. Each input goes to one output. And the same Each input goes to one output, a unique output. Think about the parabola. The parabola is not 1 to 1 because if you plug in 2, you get 4. You plug in negative 2, you get 4. That's not 1 to 1. It's every one input doesn't go to a unique output. This is 1 to 1, which is what makes it what we call invertible. It has an inverse. So this is an invertible 1 to 1 function here. So its inverse must be a reflection of this over the identity. So if I draw the identity in here, it's going to look like this. At pi over 2 up here, and at negative pi over 2 down here, I will have asymptotes. And then it'll look like this. So you know how the tangent function is restricted between negative pi over 2 and pi over 2, but its range is infinite both ways. Its inverse function is the opposite of that. Its domain is everything, but its range is stuck between negative pi over 2 and pi over 2. All invertible functions follow that. All right. More fun. Let's see. All right. Y is equal to x squared natural log arctan of x. You see product? Everyone see product? Right here? There's your product right there. Remember, this is natural log of arctangent, right? Not natural log times or anything. It's of. So that's the only multiplication you have. And so I'll apply the product rule, which will be the derivative of the first one times the second one. So 2x times everything, right? Plus
1 over tangent x.
Yeah, we have natural log of arctangent. So we have chain rule here. First derivative natural log of something is 1 over the something times, so that's the derivative of natural log of the arctangent of x, times the derivative of what's in here, which is 1 over 1 plus x squared, times x squared. Where did that come from? Finishing off the product rule. And I don't see what we could do to that other than pop that x squared up here. Maybe you could put these two together, but you'd have to put a parentheses around this, like make one big fraction out of that. Other than that, I don't see anything.
Not a whole lot you can clean up.
Yeah. All right, so it's 1:52. We are going to have a classroom activity. Yes. We don't do this very often, do we? All right. All right, so what I'm going to do is I'm going to go around the room. I'm going to put some problems on the boards around the room. And then what you're going to do is, like, this table is going to work on one problem, and then everyone around the room is going to do their own problems in groups. We're going to do that for about maybe 20, 30 minutes. All right? Sound fun? Okay. Here we go. I think I'll just make these up. So this will be your group. I'll give each group 2 problems. All right? That's 4 to the sine x. There we go. Okay, y'all can get started on that one. Let's see, where's my next group? You want to go? Okay, I'm going to put you all right here. This will be problem number 3 because y'all are going to have problem number 1. This group, but here, oh yeah, this is what I want y'all to do. I don't want y'all to write on any paper. I want you to go get a marker. I want y'all all to go up on the board, and I want y'all to talk about it. You have to, like, actually talk and work in groups. It's gonna suck. Okay.
Is that what
Next
you tell
one.
your department heads? I don't want to do this because it's going to suck.
Exactly. See y equals.
I don't want to cause it's going to suck really bad.
All right, that is yours. Let's see, this will be 5. Who wants that one? Okay, I'll have to go over here. 6. Okay.
Were you like guessing?
I'm guessing. I'm guessing. No. And then this one over here. Oh wait, this was 7. And then 8. Product. Okay, that, you know what, I'm trying to figure out. This was supposed to be yours right here.
Okay.
But I need something for this. Oh, I didn't see that board over there. You know what? How do y'all want to do this? Y'all want to go there?
Sure, why not?
Y'all want that one? I'm gonna put one more problem. Y'all figure it out. Y'all. For some reason, I didn't see this entire board here. This was actually supposed to be number 11. So. Yeah, no, I'm going to come back through and give everyone 2 problems. Hold on. You need another problem completely?
Nah, we can do it.
Let's see, one group there. Markers, I've got markers.
No, one group doesn't have one.
You don't have a problem. Yeah, we don't even have our first problem.
Here you go. If y'all need markers, just come grab one here.
Yeah.
Let's see.
You don't have a
Oh,
problem.
no. This table,
No problem.
that table, that table. Okay, I'll put yours right here. Yeah, I'll take a look. And this is number 13. Okay, have at it. Enjoy.